Hey guys, how you doing? It's Dr. Bays. This is a video on Western blotting. The science behind it would also equate to Southern blotting. The only difference is Southern blotting uses DNA and Western blotting uses proteins. So what you see here is actually an electrophoresis situation, but for a different kind of gel called polyacrylamide. It's what we use for proteins, but all the science is the same. So basically there's little wells here. You load all the wells up with massive amounts of protein, and they separate same way DNA would based on size and charge. Since proteins, by the way, do have parts of them that are positive and parts of them that are negative based on whatever amino acids are there, the sample's treated with a chemical called sodium didectyl sulfate before it's put in here, and that sodium didectyl sulfate creates a negative charge on the proteins. It kind of separates them all out in their linear form, and then it creates a negative charge, and as you know from there, the electrophoresis positive poles down here, and it will separate the proteins based on charge. So when it's finished, it looks something like this. Let me show you what it looks like, the product. It looks kind of like that. And you can see that this is the well, and they all went down here. And now the question is, with Western blotting, are any of these particular proteins a protein of interest that we want? So for example, let's just use Babesia. If we know that Babesia duncani produces a protein, and let's just say this came from somebody's blood, obviously this person's blood should not have any proteins from Babesia. So what we would do is we would have to design or order an antibody to stick to that particular Babesia protein or any other protein that we're looking for. And so here's basically the animation of how the science works. So with Western blotting, you take this membrane and it has a positive charge to it, and then from there you take your gel and you basically put the gel onto, now remember this is the polyacrylamide gel, and there's the pieces of protein that already were electrophoresed. So basically from this point all you did was electrophoresis, and you put this on this membrane that has a positive charge. Then you put another membrane on top that has a negative charge, and now you do another kind of electrophoresis where you basically turn on the electricity, and as you know, these proteins now have a negative charge because they were covered with polyacrylamide, and they're going to start to migrate down through the gel and stick to the actual membrane itself. And then basically you can peel up the gel, and the proteins are no longer in the gel. They're stuck on this membrane. And so the last part of this is, well, great. Here's a whole bunch of different proteins. Are any of these proteins the one from the Babesia duncani or for whatever we're looking for? So what we basically do is we treat it with an antibody that you can order that's specific to that particular antibody. So, or to that particular protein. So in this case, we're going to go ahead and do that. And we're going to drop in the antibody on these different pieces of protein. And you can see, of course, there's a yellow protein and there's a red one. And look in the back here, there's amino acid, or there's antibodies are not sticking to that one, but they're sticking to this. Now here's the thing, we don't know that it's sticking to that. We can't see it. So what we then do is, part of the kit, we wash everything off, and these of course stick. We add a secondary antibody that has an enzyme on it. And here comes that. And this secondary antibody is coming right in. Any second now. Here they go. So these are the secondary antibodies, and these are designed to only stick to the first antibody. So basically you're putting these secondary antibodies on the entire gel, and we don't yet know that these stuck again. So what we use to indicate whether or not this was here is we use a chemical that turns colors in the presence of this antibody, because this secondary antibody has an enzyme here, and that enzyme is going to turn this into a color. And you're going to see here comes the chromogenic substrate. Once it touches the enzyme makes a color out of it. And all that falls down here. And now you can see that if we back up the view after this particular step and we wash everything off again, we can see that out of these three proteins, this is the one that's actually present. We know that that's the Babesia duncani protein we were looking for, and these other ones are not. So that's basically the fundamentals of it. Let me show you a picture of it here. So this is a picture of a real Western blot, and all you see here, by the way, is a few of these little bands. Now understand that there were a lot of these on here, but you don't see the rest of them because these were the ones that we were looking for. So the primary antibody stuck to these bands here, then the secondary antibody stuck to them, and then the third substrate created a color and or sometimes radiation, depending on how you do it. So that is the point, and I hope you enjoyed it.